Hello, and welcome to the Deep Dive. This is where we take complex topics, look at the sources you provide, and, well, pull out the most important nuggets of knowledge for you. Today, our mission is really to get you well-informed on practical cloud security and automation. We're talking about, real-world stuff, the how-tos, and those critical configurations that can genuinely make or break your cloud setup. Our guide for this journey, it's a set of practice questions, actually, and their explanations from an industry exam, the FCSS CDS AR 7.6. Think of them as like strategic starting points, quick challenges that'll lead us into some deeper, much more valuable insights. Our goal isn't just handing you answers. It's about sparking that genuine understanding, really lighting up the why behind the best practices.
Yeah, and what's really fascinating, drawing from this kind of source material, is seeing how these seemingly small, very specific details, they directly mirror the common challenges, the best practices you see every day in modern cloud and DevOps. These aren't just abstract questions, they're practically blueprints for building resilience and security. We'll be zeroing in on how these configurations impact that bigger picture, keeping your cloud secure and running smoothly.
Exactly. So let's kick things off. We'll start with some foundational concepts, stuff that's pretty essential for any cloud pro, starting with infrastructure as code and some core networking principles. First up, Azure Bicep's architectural advantage. Let's imagine a DevOps team, right? They're adopting Azure Bicep for their IAC pipelines. They want efficiency, consistency, reliability. So what's a key architectural advantage that Bicep brings for managing their Azure resources? We're sort of weighing options around its compatibility, its deployment mechanism.
This is a really, really important point for anyone working in Azure. Bicep, well, it's a domain-specific language, right, for IC. And its strength, its core function, is that it compiles directly to a standard Azure Resource Manager template, an ARM template. Now, that's not just like a nice to have. It guarantees 100% native compatibility with the Azure platform itself.
Ah, okay. So it's not adding a layer. It's just a better way to create the native templates.
Precisely. And the big win for developers is that Bicep offers a much cleaner, much simpler syntax compared to writing raw ARM JSON. It makes your infrastructure code way more efficient to write and, crucially, to maintain. It basically streamlines the authoring. You get better readability, less boilerplate code, but you're still harnessing the full power of Azure's native deployment engine.
Okay.
So for you listening, this means faster, more reliable deployments in Azure, fewer potential errors too, because you're using a language that's optimized specifically for that environment.
That cleaner syntax sounds like a huge plus for developer experience. Makes sense. Now, just as code defines infrastructure, specific rules define network boundaries. Let's switch over to AWS. Let's dive into AWS Network ACL rule ordering. Okay, picture this. Network admin needs to temporarily allow RDP traffic. Public subnet in AWS. Sounds simple enough. But wait, there's a catch. The subnet's network ACL, the NACL, already has a rule. It's at line 100, and it explicitly denies all TCP traffic. Everything. So how do they actually allow RDP given that deny rule is sitting there? My first instinct might be, just add another rule further down. But I have a feeling that's not quite how an ACLs work, is it? Can you break down the logic?
Yeah, you've landed right on a classic AWS gotcha, as they say. Your intuition is spot on. NACLs are different. The critical thing here, the concept you absolutely have to grasp, is that NACL rules in AWS, they are evaluated in ascending order. Lowest number first, then up. And the very first rule that matches the traffic is applied. And that's it. Stop.
The first match wins. Okay.
Exactly. So if you've got that DDNY all TCP sitting at rule 100, any attempt to add an allow RDP rule with a higher number, say 200 or 300, it's completely useless. The traffic hits rule 100, gets denied, and never even gets evaluated against rule 200.
Ah, right. It just stops there.
It stops dead. So to make this work, to actually allow RDP, the admin must insert a new allow RDP rule, but with a lower number. Something like rule 50 or 90, whatever is available below 100. That way, the RDP traffic hits the allow rule first, it gets processed, and it never even reaches the BENY at 100.
So order is everything.
Everything. We've genuinely seen major outages where teams have spent hours, literally hours, troubleshooting what they thought were phantom network problems, only to eventually find a single misplaced NACL deny rule blocking critical traffic for every single instance on a subnet. Understanding this rule ordering isn't just about security ticking boxes, it's fundamental for operational stability. You avoid those unexpected service drops.
Wow, that real-world example really drives it home. Such a subtle detail, but massive consequences. Okay, from that foundational logic, let's jump into some of the powerful tools protecting our cloud frontiers. We're talking next-gen firewalls, cloud-native security services. Let's look at FortiGate, NGFW, and containerized environments. How can a FortiGate, a next-generation firewall, actually boost security for a containerized application?
Yeah.
Specifically thinking about Kubernetes here, we're looking for two key ways it offers protection.
Right. This is a great example of how traditional, powerful security tools are adapting to these modern, really dynamic environments like Kubernetes. So FortiGate NGFW enhances container security in two really crucial ways. First, it can be configured to inspect what we call east-west traffic. That's the traffic moving between containers inside the Kubernetes cluster itself.
Internal traffic.
Exactly. Absolutely vital in microservices setups, where a breach in one tiny service could potentially spread laterally to others. Detecting and stopping that internal spread, that's a core strength. Second, FortiGate provides really robust north-south traffic inspection. This is the traffic entering and leaving the container environment from the outside world.
That's the perimeter defense.
That's your perimeter, yeah. Protecting the whole cluster from external threats, controlling what data goes out. It's about having both that strong outer wall and internal segmentation. Now, it's important to note, it doesn't directly scan the container images themselves or the source code that's usually handled by different tools earlier in the pipeline, like a SCA tool, perhaps.
Which leads us perfectly into our next point.
Right. But the FortiGate brings that sophisticated firewall intelligence, that deep packet inspection, into the fast-moving world of containers, giving you real visibility and control over those network flows.
That dual capability, internal and external, sounds incredibly valuable for containers. Okay, staying in this DevSecOps space, let's talk about stopping vulnerabilities before they hit production, especially focusing on, well, all that third-party code we rely on. Let's discuss FortiDevSec for third-party library vulnerabilities. So an organization, they're using FortiDevSec. It's plugged into their CI/CD pipeline. The security team's big priority, making sure all those third-party libraries, the open-source stuff they pull into their containerized apps, are free of known vulnerabilities. Before deployment, critical step. Which FortiDevSec feature is really designed for this specific, crucial task? Because we know these libraries are a huge attack surface, right? How do you get a handle on that?
Yeah, absolutely huge. And this is exactly where FortiDevSec software composition analysis, or SCA, comes into play. It's the star here. SCA tools are purpose-built to identify vulnerabilities and often license compliance issues, too, within those third-party libraries and dependencies. All the external packages, the open-source components your apps depend on, SCA scans them against databases of known vulnerabilities, flagging problems before they get baked into your deployable artifact.
Okay, so it's different from SAST or DAST then.
Totally different. SAST, static analysis, looks at your own source code for bugs and potential flaws. DAST, dynamic analysis, tests the application while it's running. A container scanner might look at the container's configuration or maybe the OS layer within it, but SCA specifically targets the contents of those third-party packages you've included.
Got it.
So for you, the listener, relying on external libraries without doing SCA, it's like building your house on, well, potentially shaky ground, even if your own bricks are perfectly laid. SCA is that essential quality control check for all the stuff you didn't write yourself. It catches those issues early, dramatically cutting down your attack surface before anything goes live.
That's a massive point. The attack surface isn't just your code, it's everything you build on. Okay, speaking of identifying issues, let's shift gears slightly to incident investigation within AWS. For our next deep dive, let's set a scene. The security analyst is digging into a potential incident. It's on an EC2 instance in AWS. They urgently need to see the metadata of all the network traffic, things like, source and destination IPs, the ports, the protocols, everything going to and from that specific instance. What's the go-to, the most appropriate native AWS service for reliably collecting this vital network intelligence?
Oh, for network traffic metadata in AWS, the answer is definitely VPC flow logs. They're absolutely indispensable for this. They're specifically designed to capture metadata about all the IP traffic flowing within your AWS virtual private cloud. And they capture exactly what that analyst needs. Source IP, destination IP, source to destination ports, protocol numbers, packet counts, byte counts, and crucially, whether the traffic was accepted or rejected by security groups or NACLs.
So it sees the decisions made by security groups and NACLs too.
Yes, that accept reject status is key. This data is just invaluable for security investigations, for troubleshooting network connectivity problems, even just for understanding your normal traffic patterns to spot anomalies later. And it's really important to distinguish flow logs from other AWS logging and monitoring services like CloudTrail. That logs API calls. It tells you who did what API action when. Very different.
Right. Admin actions versus network flow.
Exactly. And CloudWatch is mainly for performance metrics, CPU, memory, disk I/O, and for collecting application-level logs. But for tracing the actual network activity, understanding those communication paths, figuring out who talked to whom and when. VPC flow logs are your eyes and ears right there on the network. They provide that raw data needed to trace activity and figure out what happened during an incident.
Makes sense. Essential tool for any investigation. All right, let's step it up a notch now. We're going to dive into some more intricate architectural challenges and also deployment strategies in the cloud. This next one, it's a bit of a sophisticated routing puzzle, but incredibly practical for anyone managing larger scale networks. Let's tackle AWS Transit Gateway, TGW, hub and spoke routing. Okay, picture a complex setup. Hub and spoke topology using AWS Transit Gateway. There's a central security VPC. It's got a FortiGate firewall in it, acting as the hub. Now, the spoke VPCs, these host the actual applications they need to route all their non-local traffic through that FortiGate in the hub for inspection. Centralized security, right? This is a tricky multi-select question. We need to pinpoint 3 absolutely mandatory routing configurations to make this whole thing work. This is where the details of routing tables really matter.
Oh yeah, this scenario is a perfect example of how interconnected routing rules have to be. It's absolutely essential for achieving that centralized security in complex multi-VPC cloud setups. So to make the specific flow work, 3 distinct configurations are mandatory, and they really work together like a chain reaction. First, the spoke VPC subnet route table needs its default route, that's 0.00 pointing to the TGW. What this does is tell every instance inside those spoke VPCs, if the destination isn't within this local VPC subnet, send the traffic over to the transit gateway. That's step 1, getting all non-local traffic out of the spoke and towards the hub.
Okay, step 1, spokes point to TGW.
Step 2. The TGW route table that's associated with the spoke VPC attachments. That route table needs its default route, 0.0.000 pointing specifically to the FortiGate attachment. So the TGW gets the traffic from the spoke. This rule then tells the TGW, okay, for anything going outside the defined spokes, basically, internet-bound traffic or maybe traffic to other spokes, send it over to the FortiGate in the security VPC. This forces the traffic through the firewall.
Got it. TGW sends non-local spoke traffic to the FortiGate.
Right. And finally, step 3, and this is crucial for the return path. The TGW route table associated with the security VPC attachment, where the FortiGate lives, must have static routes for all the spoke VPC CIDR blocks, and these routes must point back to the FortiGate attachment. Think about it. After the FortiGate inspects the traffic, maybe allows it, it needs to send the response back to the original spoke VPC. This route table tells the TGW, if traffic is destined for spoke VTCA's address range, send it via the FortiGate attachment, which knows how to route it back there. Without this, return traffic just gets lost.
So the TGW needs routes back to the spokes via the FortiGate.
Precisely. So those 3 pieces together, spokes to TGW, TGW to FortiGate for default, and TGW knowing how to get back to spokes via FortiGate. They create that complete loop. It ensures all non-local traffic from every spoke. VPC absolutely has to pass through the FortiGate for inspection. It guarantees your security appliance is always in the path.
Wow, that is a detailed dance of routing tables. Really highlights the precision needed for these more complex cloud architectures. Okay, shifting from routing complexity to deployment smoothness, let's talk about updates without causing user headaches. Next up, AWS CloudFormation for minimal downtime updates. Okay, and admin is using AWS CloudFormation. They manage a multi-tiered application stack with it. Now, they need to update the stack, maybe roll out a new version of an EC2 instance AMI, but the key requirement is minimal downtime during this deployment. Which CloudFormation feature should they be using to manage this update effectively and safely?
Yeah, this really shows how CloudFormation is much more than just a tool for initial provisioning. It helps manage the entire lifecycle, including updates, really sophisticatedly. The key feature here is using the update stack command, but crucially, combining it with the right update policies. Policies like auto-scaling rolling update or specific replacement policies for certain resource types. These policies let CloudFormation perform controlled rolling updates. It can replace old instances with new ones gradually, maybe maintaining a certain capacity level throughout, or perform blue-green style replacements. This is exactly how you achieve minimal, or sometimes even 0, downtime during your deployments. You seamlessly swap the old for the new without interrupting service.
So it's not just apply changes, it's apply changes intelligently.
Exactly. It provides that orchestration layer for the update process itself. Now, you mentioned other options, like change sets. They're great, but they only preview the proposed changes. They don't execute the update or manage the downtime aspect.
Review only.
and drift detection. That just tells you if your deployed stack has diverged from the template. It identifies configuration drift, but it's not a deployment tool itself. CloudFormation's update policies are what give you that granular control needed to evolve your infrastructure gracefully without taking everything offline. For you, the listener, ensuring high availability during updates is usually paramount, right? Mastering these policies means you can roll out new application versions or infrastructure changes without your users even noticing.
That's a critical capability for pretty much any production system. Okay, let's bring this home. We're moving into some essential insights now on secure authentication, cloud compliance, and making automation efficient. Next, Azure Managed Identity for secure authentication. Administrator is setting up an Azure SDN connector. It's on a FortiGate, and they want to use a managed identity for authentication to Azure. Good practice, right? No stored credentials. They've configured the FortiGate side correctly. They're sure of it. But the connection keeps failing. Authentication error. They've triple checked the FortiGate config. What's a likely misconfiguration? Something maybe missed on the Azure side that's stopping this managed identity authentication from working. We love the idea of credentialless auth, but sometimes there's that one checkbox.
Oh, this is such a common stumble when people first start using managed identities in Azure, even though they're a fantastic security improvement. The absolute most likely culprit here is that the system-assigned managed identity simply hasn't been enabled for the FortiGate's virtual machine within Azure itself. You see, for a VM or another Azure resource, to use a system-assigned managed identity, you must explicitly go into the Azure portal or use CLI/IC to switch that identity on for that specific resource. It's like flipping a switch. If that switch isn't flipped, the identity fundamentally doesn't exist for that VM to use. Azure doesn't know to associate the identity with that VM. So even if the FortiGate is configured perfectly to try and use it, the authentication fails because Azure doesn't recognize the VM as having that identity enabled.
So it's not enough to just configure the service using the identity. The resource itself needs the identity turned on in Azure.
Exactly that. It's a prerequisite. While sure, other things like expired service principals or wrong tenant IDs can cause auth issues, in this specific case, managed identity failing despite the client config being okay. The most common oversight is forgetting to enable the identity on the Azure resource itself. It's a small click, but it's the foundational step for this whole mechanism to work.
That is a perfect example of a small setting with big consequences. Easy to miss if you're new to it. Okay, let's shift to protecting data, specifically in cloud storage, and hitting those compliance goals. Our next deep dive is on FortiCNP for S3 malware and sensitive data scanning. An organization, they need to protect their S3 buckets. Two key things: protect them from malware being uploaded and automatically find any sensitive data that might be stored in there, for compliance reasons like GDPR or PCI. They're looking for a single FortiCP feature that can handle both of these jobs. It's a double threat, right? Malware coming in, sensitive data potentially leaking out. What's the tool for that?
Yeah, tackling both security and compliance in storage is critical. And for this dual challenge within FortiCNP, the feature you're looking for is FortiCNP data scan policies. These policies are specifically designed and engineered to scan S3 buckets comprehensively for both malware signatures and patterns matching sensitive data types. Think PII, financial data, health records, custom patterns you define. So it directly hits both requirements: the security angle of stopping S3 from becoming a malware distribution point, and the compliance angle of identifying and helping you manage or protect sensitive information that shouldn't be there or needs extra controls.
Okay, so it's not just finding risks, it's actually scanning the data content for these two specific things.
Exactly. While other FortiCNP policy types might focus on configuration risks or automating remediation actions or general threat detection based on activity logs, the data scan policies are the ones that combine these two specific, crucial content scanning functions: malware and sensitive data detection. It's a really powerful combo, simplifying what could otherwise be a very complex task of securing your data and meeting those data governance rules in your S3 environment.
Combining security scanning and compliance scanning in one feature definitely sounds efficient. Okay, finally, let's touch on automation fundamentals, making things repeatable and reliable. For our last deep dive, let's look at Ansible minimum files for VM deployment. Okay, you've been tasked automate deploying a group of FortiGate VMs. You're using Ansible. You've done the hard work. You've created a brilliant playbook, got all the necessary tasks to find in there. So the question is, beyond that playbook YAML file itself, what is the absolute minimum number of additional files you need for Ansible to actually run this playbook and deploy those VMs? And what's their basic purpose?
This question really cuts to the core of Ansible's, elegant simplicity, I think. Beyond the playbook, which, as you said, defines what tasks need to be done, Ansible absolutely requires just one additional file, an inventory file. That inventory file's job is simple. It defines the target hosts. It tells Ansible where to run the tasks defined in your playbook. In this specific case, it would list the FortiGate VMs you want to configure or deploy. It's basically Ansible's address book.
Just the inventory. What about variables files or roles?
Right, so things like variables files, super common, highly recommended for managing dynamic data like IP addresses or passwords separately from your tasks. And roles directories, absolutely essential for organizing larger, more complex Ansible projects into reusable components. But are they the minimum requirement just to get a playbook to execute against some hosts? No. Technically, you could hard code everything in the playbook, though that's bad practice, and run it against an inventory. The playbook tells Ansible the what, the inventory tells it the where. That's the bare minimum.
What and where. Simple as that.
Pretty much. Understanding those minimal core components, playbook and inventory, is really key for anyone just getting started with Ansible automation. And make sure your automation is targeted correctly and can actually run.
So what does this all boil down to for you, listening? Well, as you navigate your own cloud journeys, maybe consider this. How might a seemingly minor configuration detail, maybe something like the ones we touched on today, be the single point of failure, or perhaps the critical enabler for your entire cloud security strategy? And how often, maybe in the rush of daily work, do we overlook these small but mighty elements thinking we've handled all the big picture items? Keep exploring, keep asking those questions, and definitely keep building securely. Thank you so much for joining us for this deep dive. We'll catch you next time.